G'day boys, welcome to Stem19, which is also the commencement of our Core 2 studies. Now this STEM is looking at the energy systems, of which there are 3. And you can see them listed here on the left, and we will look at them in the context of these 6 headings here, which is why you've drawn up those tables in your books. Now, you can get pretty in depth with energy systems. We don't need to in this course, we just need to focus on a bit of background info and also these 6 areas. So, before we get into the systems, we just need to quickly look at this molecule called adenosine triphosphate. Now that's the chemical compound that the body uses to produce energy, and it's actually sitting in your body stored, ready to go. So that's why you can go from a standing start to sprinting straight away without having to wait for any energy supplies to arrive. So it's literally sitting there ready to go. This is what the ATP molecule looks like. It's 1 part adenosine, 3 parts phosphate. And where we get the energy from is where this bond here between the 2nd and 3rd phosphate molecules actually breaks off, and the byproduct of that is energy. It also gives off heat, which is why we warm up when we're exercising, or why our body temperature increases when we exercise. So by breaking that bond off, that's what gives our muscles the ability to contract and create movement. Now that this bond has been broken, we're left with adenosine diphosphate, because we've got 1 part adenosine, 2 parts phosphate. And what the body needs to do is attach this 3rd phosphate back to the 2nd one to give us ATP again, so that our body can actually use energy again. Otherwise, if we just relied on our stored energy, we'd only be exercising for probably 3 seconds, 3-4 seconds, and then we'd be coming to a dead stop. So what we look at in the energy systems is how each system gets adenosine diphosphate back into adenosine triphosphate by resynthesizing this bond. So that process is called resynthesis. Now, moving on, these are the 3 energy systems again. Now, this diagram shows that 2 energy systems, which are the A-lactic acid and the lactic acid system, work anaerobically, which means without oxygen, and 1, the aerobic system, works aerobically, which means with oxygen. And that plays a significant role, which you'll see a little bit later on, in terms of energy production. That being oxygen, it's a crucial ingredient. Now moving on, here's our yields of food, various foods. You can see here fat has more than double the kilojoules of carbohydrates, but it actually requires nearly double the amount of oxygen for our body to use it. So it's not very efficient. That's why our body goes to burn carbohydrates straight away. In the aerobic system, of course, we're talking here. So in your notes you've done this table, and we'll just speak about each system individually. So here's your background information on the ATP-PC system. We'll look specifically at the table and what happens. Okay, so going through the 6 areas. The source of fuel, ATP-PC, is creatine phosphate, which is stored in the muscles. Is it considered efficient? Well, it's efficient in that energy is produced instantaneously, and the recovery time of the creatine phosphate stores is relatively short, but it's not really considered efficient because it only lasts for 10 to 12 seconds, as you can see here. If this system lasted as long as the aerobic system, it would be brilliant because it's got no negative byproducts. Now, this system, as I mentioned, it operates for 10 to 12 seconds only. And what causes it to fatigue is the fact that the body will exhaust the supplies of creatine phosphate that's stored inside it. The byproduct of the ATP-PC system is heat. The process of recovery takes about 2 minutes, and what happens is the body's stores of PC need to resynthesize back together again because in resynthesizing the ATP, this creatine phosphate actually splits. So it goes from 1 joint molecule of creatine and phosphate to 2 split molecules of creatine and phosphate, so they're 2 separate ones. And the energy from that split actually enables the ATP molecule to be resynthesized. So what the body needs to do is wait for these stores of PC to join back together again, and that takes about 2 minutes. So that's the ATP-PC system. So used for a very short duration and at high intensity. So it's used obviously at the very, very start of exercise, but it can also be used in the middle, say, of a marathon. If a runner decides to put on a sprint and increase the intensity of their exercise, they will go to the ATP-PC system predominantly, and then into the lactic acid system if that sprint lasts longer than 10 seconds. So that's the first energy system. The next one is the lactic acid system, and here is the background to it. And what happens here with the lactic acid system is it actually uses glycogen. Now the start of this system is actually exactly the same as the aerobic system. So it uses glycogen, which breaks down into glucose. That then enables 1 or 2 molecules of ATP to be resynthesized, which is okay. That's not too bad. The byproduct of this is this thing called pyruvic acid. Now pyruvic acid in itself is not a problem, but if there is insufficient oxygen in the muscles, then this pyruvic acid actually gets turned into a waste product called lactic acid, and this lactic acid is what causes the fatigue. Okay, so again, this system is working anaerobically, which means without oxygen, and that's a huge consideration, because without the oxygen, you can see here it says insufficient oxygen, we get lactic acid. If there was sufficient oxygen, we'd get something else, and then that would be the aerobic system. So it resynthesises about 1 to 2 ATP molecules. Now just having a look at the specific table. Oops. So the source of fuel here for the lactic acid system, carbohydrates, which are in the form of blood glucose, and also the glycogen stored in the muscles. How efficient is the energy production? Well, it only yields about 5% of the number of ATP molecules that are produced when oxygen is available. So it's pretty inefficient. Again, it's used at high intensities. So in the middle of a race, again, we use that analogy. If a marathon runner puts on a sprint, he uses that ATP-PC system. That runs out. He can still keep sprinting, but he'll now be working in the lactic acid system. So still working anaerobically, but you can't work in the lactic acid system for too long, because too much lactic acid will build up, causing fatigue. So as I mentioned there, it's not really very efficient, because it only yields about 5% of the number of molecules that are found in the aerobic system. How long does it last for? Well, if you're going full on at high intensity, it'll be about a minute, and then you will have to stop, because you'll be that fatigued and there'll be that much lactic acid in the body, you will not be able to go on. If you're going about moderate intensity, it'll last for around about 3 minutes. So that sort of is like at the start of a race. The runner will not necessarily be working anaerobically, but because oxygen hasn't arrived yet, they'll still be working. Sorry, they won't be working at a really high intensity, but because oxygen hasn't arrived yet, they'll still be working anaerobically. So you can go for up to 3 minutes there if it's a moderate intensity. And if intensity is sub-max, moderate is sort of around 70–75%. If intensity is sub-maximal, this system can last for more than 3 minutes, because there's not too much lactic acid being built up. So there's no concrete time frame for this system to last for, because it depends on the intensity. So obviously the higher the intensity, the more lactic acid gets built up, the shorter you can use this system for. What causes fatigue? The accumulation of the lactic acid, and also these hydrogen ions that actually increase the acidity of the muscle cells. And as soon as the acidity level in muscle cells increases, then fatigue kicks in. Now the byproducts is pyruvic acid, which, as I mentioned before, because of the lack of oxygen, turns into lactic acid, and also these hydrogen ions, which, as I just mentioned, they're the cause of fatigue. So the byproducts of this system are actually the things that cause it to fatigue. Now, how does it recover? It takes between 20 minutes to 2 hours for lactic acid to be removed from the blood, and again, that will depend on the intensity of exercise that you've done and how long you've been going for. So obviously, if it's moderate intensity exercise, there's not going to be that much lactic acid accumulated as opposed to high intensity exercise. Recovery is also enhanced if there's an active cool down completed, which is done at about 40 to 50% of maximum heart rate. So that is the lactic acid system. Now the aerobic system can be quite complex. We'll have a look. This is obviously the background information for it. We'll have a look at this in diagrammatical form. But you see over here on the right-hand side, the glycogen in the muscles or liver break down into glucose. This then resynthesises 1 ATP molecule, or 1 or 2 ATP molecules. The byproduct of that resynthesis is this pyruvic acid. Now that is exactly the same as the start of the lactic acid system, if you remember back to that one. The key difference is this ingredient here. Oxygen is added to the pyruvic acid, which forms this acetyl coenzyme A. Now what that does, it actually triggers a complex series of chemical reactions called the Krebs cycle, which in turn, that will resynthesize another 30 or so ATP molecules. Byproduct of this Krebs cycle is carbon dioxide, and that is actually exhaled by the lungs. So if you think back to the lactic acid system, the lactic acid is a byproduct, and our body can't really do too much with that. Here in the aerobic system, the byproduct is carbon dioxide, and we can actually breathe that out, so our body's not poisoned by it. Now, we move, after the Krebs cycle, we move on to the electron transport system, where we have, because we have hydrogen and electron atoms, and these actually split, and we use the electrons to resynthesize more ATP. The hydrogen forms up with leftover oxygen, and that becomes water. And our body is actually able to use that to decrease the acidity in the muscle cells and also cool things down, which is the purpose of water. So not only are we getting more ATP molecules out of this system simply because we added oxygen, but the waste products are actually, or this one, carbon dioxide, is breathed out, and water is actually used by the body, so it has a practical purpose. For you guys, this can all be pretty confusing. You just need to be aware that simply by adding oxygen, you can resynthesize in the region of probably another 30 plus ATP molecules, which is why this system is considered extremely efficient. Here, over on this side, this is what happens with the fatty acids. They're in the form of triglycerides. They get broken down to fatty acids, and then they form, or they start this Krebs cycle. This process over here is called aerobic glycolysis. In the lactic acid system, that's called anaerobic glycolysis. Now here you've got proteins, and it says they break down to amino acids, which they do, and they can also be used for fuel, but that's only in extreme circumstances. So here's your table for the aerobic system. Source of fuel, carbohydrates in the form of glucose. Can also use fats after a period of time, in extreme cases protein, but that's, you're going into pretty dangerous territory there. It's very efficient because you get significantly more ATP molecules out of it, and also the waste products. Like I said, carbon dioxide is breathed out, and the water is used by the body. So it's very, very efficient, the most efficient system. How long can it operate? Well, it takes about 2 to 3 minutes to kick in because the body needs to deliver the oxygen, but once it's working and you're in steady state activity, at a low intensity, the supply of energy is virtually endless. So it's a very, very efficient system. What causes it to fatigue are the complete depletion of your carbohydrates and fat stores, and that would be, think about that. That would be a pretty significant thing if you're able to deplete all those stores. The byproducts, carbon dioxide, I've already mentioned, and water, also heat, but every energy system produces heat. So those two byproducts are actually not a problem because, as I mentioned before, one's breathed out and the water gets used. How does it recover? It depends on how long the activity's gone for and what sort of strain you've put on the system. If you, for example, a marathon runner, that could take them a good few days to replace lost glycogen and so on. But as opposed to someone who just jogged for 30, 40 minutes, that would probably only take 1 or 2 meals, and they would have their energy levels back. So that's the 3 energy systems. I hope you enjoyed the presentation as much as I did.